College of Engineering and Technology presents online spoken faculty development program on Advanced Communication Laboratory, experiment number 4, session 3, study of eye pattern in fiber optic digital link using PRBS Generator, model MS Tester EPS04. PSNA College of Engineering and Technology presents online spoken faculty development program on Advanced Communication Laboratory, experiment number 4, session 3, study of eye pattern in fiber optic digital link using PRBS Generator, model MS Tester EPS04. So in this section we are going to detailedly study about the eye pattern of the tester EPS04. It is the introduction photo of tester EPS04, which described here is an optimized setup to conduct a comprehensive study of eye pattern or eye diagrams of a fiber optic digital transmission system. The tester EPS04 is centered around two popular and prone optical fiber digital transmission micromodules that have been in use for 20 years. This model designated DHM T660 digital transmitter and DHM-R HS digital receiver are described at length. The models are terminated with industry standard SMA receptacles that facilitate coupling with SMA-SMA connectorized PMMA plastic optical fiber F4F cables. Industrial grade Teflon insulated electrical wires are employed in the models for reliability and durability. The wavelength of operation is 660 nanometer. The other key features of tester EPS04 is the built-in pseudo-random bit sequence generator that can be set for operation at baud rate of 2.5 megabits per second, 1 megabits per second and 500 kilobits per second. The microcontroller-based PRBS generator is described in the upcoming section. The microcontroller uses a 20 MHz crystal for high timing stability. Output waveform is settable through a single push button switch. Tester EPS04 includes a 1 meter SMA-SMA connectorized PMMA cable. The only other T&M equipment required is a dual channel 20 MHz oscilloscope, both analog and digital, with matching probes. On oscilloscope that has settable persistence will be an added advantage. And this is our fiber optic micromodules for digital transmission models DHM T and DHM-R. In the top of the diagram, the models indicated by the DHM T660 and DHM-R. So both ends are connected with the SMA connector. In the bottom of the figure indicates how the transmitter and receiver connected via PMMA fiber cable. In this section, we are going to detailedly study about the basic information about the micromodules and specification of the DHM transmitter receiver, working principle and application. General information about the micromodules. The fiber optic micromodules DHM T660 and DHM-R compresses two encapsulated with Teflon insulated leads. Device that transmit TTL signals through a multi-mode step index plastic fiber at 660 nanometer. The fiber optic modules employ SMT technology to achieve a high degree of reliability and compactness. Industry standard fiber optic SMA connectors provide for rigid and consistently repeatable operation. And the specification of the DHM transmitter and receiver which support and operated at the wavelength of 660 nanometer fibrous PMMA step index or multimode. Connector used here is SMA. Cable length will be 1 to 10 meters. Optical power is 80 microwatt peak. Power supply is 5 volt DC. V in and V out is TTL compatible 0 to 5 volt and speed will be DC to 5 megabits per second minute. And working principle, the DHM model requires external 5 volt DC power supply, digital signal generator and a PMMA patch cord terminated with SMA connectors. On the transmitter side, there are no external settings. The LED current when on is approximately 50 milliamps. When off, it is 0 milliamps. On the receiver side, VTH sets the threshold detection level for internal comparator. Using this, the rise time and fall time distortion may be suitably set. RN sets receiver gain and bandwidth by adjusting RN to around 2500 ohms and also suitably trimming the VTH. One can achieve good rise and fall times. Please note that the VIN is TTL signal and Vout is TTL compatible. And the application of the DHM transmitter receiver model is it is used in the Telenet system employing these devices in TNS20ED to design and evaluate digital optical links. And second application will be for optical communication encoding technique side. So in this section, the tester EPS04 detailedly described. The tester EPS04 is compressed by the many component. This is a schematical diagram only. We can see detailed in the next slide using the kit type. And this is the fiber optic digital link using PRBS Generator model MS Tester EPS04 which is compressed by the main component, that is the transmitter and receiver, along with the PRBS Generator waveform from square wave 0.5 megabits per second, 1.0 megabits per second, 2.5 megabits per second. In the left hand side, we have the pin as V in, VPO and Vout. And we have the VTH in the down portion, and we have the one more push button to select the PRBS generator waveform. So these are the component is compressed in the single kit of the I pattern study. Next we are going to detailedly study about what is the transmitter section and what are the pins are involved and what is the receiver section and what are the pins are involved in the receiver section detailedly along with the PRBS generator waveform. So in this section we are going to detailedly study about the fiber optic digital transmitter. The transmitter unit converts input digital electrical signal, that is TTL CMOS, to optical signals for transmission through on optical fiber. The DHM T 660 micromodule converts electrical signal to an optical output by driving the FO LED to cut-off condition for state 0 and to full on condition for state 1. The circuit is designated to provide fast turn on and turn off of the FO LED. Optical power is coupled to the optical fiber through an SMA connector. Next, we are going to detailedly study about what are the pins are involved in the transmitter side. The first pin will be P0, that is output power. This is on SMA connectorized optical output port. The SMA connectorized PMMA cable connects the transmitter to the receiver. The second pin will be VIN. This is a TTL compatible input. Speeds range is from 0 to 5 megabits per second. The input may be a simple square wave or a complex pseudo-random bit sequence from a function generator. In this trainer, the output of the controller, that is microcontroller, PRBS out pin number 17 is internally connected to VIN and hence no external VIN should be applied to it. VIN connected to CH2 will be used as the reference waveform for the case of an ideal I pattern as well as the trigger source in the course of this study. One may choose to use CH1 for this purpose instead. So next we are going to study about what are the selected mode used for the PRBS generator. The select switch, this push button switch facilitates selection of the 4 type of waveforms in the sequence shown below. At the end of the 4th selection, the circle repeats. The operation will be power up, first press, second press and third press and fourth press, and the respective waveform and baud rate and speed along with the pulse width is displayed here. And the last pin will be the ground. The 2 terminal marked ground or the common system ground. So in this slide we are going to see about the fiber optic digital receiver. The signal at the far end of the optical fiber cable is coupled to the optical port P-in through on SMA connector. The micromodule DHM-R HS converts the input optical signal into a TTL compatible electrical signal employing a free amplifier followed by a high speed comparator. The bandwidth of the received signal is determined by the input resistance Rin. In our study, the internal Rin of 5.1 K will remain unchanged. Next, we are going to study about what are the pins are involved in the digital receiver. The first pin will be P-in. This is the optical input port terminated with an SMA receptacle that mates with the SMA connectorized PMMA cable. And second pin will be Vout. This is the TTL compatible output from the built-in high-speed comparator. And third pin will be VPO. This is the analog interstage output that precedes the preamp and the high-speed comparator stages. It provides for setting receiver gain and bandwidth. The built-in Rin is 5100 ohms. The system gain is directly proportional to the value of the Rin and given by G Rin, that is equivalent to K V0 Dig divided by Rin. Rin may be set in the range 1000 to 5000 ohms through external fixed metal film resistors. The system bandwidth and rise time are related and or inversely proportional to Rin. Proper selection of the Rin determines optimum bandwidth or rise time and gain. For the I pattern studies in this slide, Rin will not be changed. And the next pin will be the VTH. This potentiometer sets the threshold for the comparator. This voltage is settable in the range of 0 to 600 millivolt. The shaping of the TTL output waveform is done with this. The best performance is achieved for VTH is equivalent to 0.5 VPO. Next important section in this kit is PRBS generator. The PRBS generator is specified with the different important parameter along with the operation waveform, baud rate and pulse width. The operation waveform, baud rate and pulse width is already explained detailedly in the previous slide. So we are moving into the next slide. Basic fiber optic digital link setup. The procedure to set up a basic digital transmission system with the Tester EPS04 and evaluate of the same is discussed here. The basic setup will be used for all other studies in this experiment. The procedure to set up a basic digital transmission system with the Tester EPS04 is compressed by the many steps. The first step, turn the tester on, connect the optical cable as shown the diagram, connect the oscilloscope CH2 to Vin and CH1 to Vout. Use CH2 as the trigger source for the oscilloscope. Step 2. Select the square wave mode in the PRBS waveform generator. Set oscilloscope time base to 400 nanosecond per division. Set Y amplifiers of both channel to 2 volt per division. Observe the square wave on CH2. And step 3. Gradually increase VTH from the minimum position, that is extreme counterclockwise position. Observing waveform on CH1. Initially, no signal will appear on CH1. As VTH increases, waveform on Vout will appear. Set VTH to match pulse width of the transmitted and the received waveform. To do this, closely observe the two waveforms and fine-tune VTH. When this is done, the digital link has been set up for optimum transmission. VTH may be left undisturbed unless otherwise specified. Please note that there will be a delay between the transmitted train, that is Vin, and the received train, that is Vout. And the step 4, measure the rise time TR of the transmitted and received pulse. TR is the time taken for a pulse to rise from 10% to 90% of its amplitude. Next, measure TF of the transmitted and received pulse. TF is the time taken for the pulse to fall from 90% to 10% of its amplitude. Next, measure PT, that is the propagation delay, which is the time delay between the rising edges of the transmitted and received pulses, assuming equal pulse width. While the PT will be around 200 nanosecond, TR and TF will be in the region of 20 to 40 nanosecond in both cases. The screenshot from a DS4 depicted the waveform captured. TR is equivalent to TF, that is equivalent to 40 nanosecond, and propagation delay is 200 nanosecond. So still now we have explained the detail is depicted in this waveform. So here channel 1 is connected to the Vout and channel 2 connected to the Vin to observe the pattern for the fiber optic digital link basically. So next we are going to study about the I pattern for the optical fiber digital link. It is the introduction of the I pattern we are going to see now. serial data transmitted through one optical fiber digital transmission system suffers distortion and impairment, traveling from the transmitter to the receiver. Distortion caused to the signal amplitude and time related parameters severely affected and limit the performance of the system in terms of transmission bandwidth and distance. A rapid and effective method of assessing the performance and quality of the transmission system is to employ the eye pattern techniques. An oscilloscope is employed to generate an eye pattern by overlaying sweep of different segments of a long data stream controlled by a master clock, which may be used as the oscilloscope trigger source. The stream of output pulses from the transmission system resulting from a pseudo-random bit sequence generator at the input creates an eye pattern when the zeros and ones are superimposed. By adjusting the persistence of the oscilloscope suitably, an eye pattern as shown in this diagram is displayed on the scope. Differences in timings and amplitude from bit to bit result in spread of these parameters. Various transmission parameters may be assessed visually from the eye diagram. An ideal digital transmission system will have a rectangular eye pattern fully open. With increase in timing jitter and amplitude variations, the eye opening begins to string. Eye pattern opening begins to string. The transmission parameter that can be assessed employing an eye diagram are shown in this slide. In this slide, we are going to see about the procedure to generate the eye pattern on V out and V in. The first experiment will be to set up the eye pattern for the input V in and the output V out of the optical fiber digital link after initially set up the basic digital link for optimum performance. As described earlier, the experiment will be conducted with PRBS speed of 500 kilobits per second, 1000 megabits per second and 2.5 megabits per second. Measurement may be recorded in the oscilloscope or DSO. Step 1. Set up the optimum digital link as described in detail in the early chapter. Step 2. Next select to the 500 kilobits per second mode. Set oscilloscope sweep rate to 1 microsecond per division. The Y settings of the scope may remain unchanged at 2 volt per division. The trigger source 2 may remain on CH2. Step 3. Now increasing the persistence settings of the oscilloscope to a high value as possible. In a DSO, 10 seconds will be reasonable. In analog oscilloscope with no persistence control, one may increase the intensity until a pattern shown in the next slide appears. The eye patterns for the transmitted train V in on CH2 and received train V out on CH1 will have close resemblance. In this experiment, we have familiarized ourselves with the oscilloscope setting required to generate an eye pattern. The eye pattern generated for V in and V out are almost ideal in that the rectangular eyes are fully open other than the eye width and the eye height. Other measurement may not be true meaningful. In this diagram, that is the observation result, we can observe the eye pattern of V in and V out operated at the PRBS Generator waveform mode as 500 kilobits per second. The CH1 connected to Vout and CH2 connected to Vin, and you can easily identify what is the I pattern diagram appear in both categories. Step 4. Now set select to 1 megabits per second mode. Next set the X sweep rate of the oscilloscope to 400 nanosecond per division. Keep all other settings unchanged. Note that the oscilloscope pattern should be close to the I pattern diagram appears in the next slide. So in this slide, I pattern of Vn and Vout for the PRBS 1 megabits per second is observed at the CH1 Vout and CH2 Vin. In this experiment, change in the I patterns of Vin and Vout is a bit more noticeable. The rise and fall times are more significant, still not measurable. The phase or the timing jitter on Vout is a little greater than that on Vin. At a baud rate of 1 megabits per second, the performance of the digital link is close to being ideal. In that, the received drain Vout is almost identical to the transmitter drain Vin, except for the propagation delay equal to 200 nanosecond. In this DSO, the observation of the I pattern of Vin and Vout at the operating mode of the PRBS generator is 2.5 megabits per second, where channel 1 is connected to Vout and channel 2 is connected to the Vin, and the respective I pattern is clearly visible in this slide. Notice the change in the I pattern of Vin and Vout, which from being rectangular at lower baud rates has now closed. The rise time TR and fall time TR are now measurable from the Vin I diagram. They can be estimated at 30 to 40 nanosecond. Timing jitter is in the magnitude, often Vout is in the region of the 40 nanosecond. Please notice that Vin also has a timing jitter. This is due to the limitation of the PRBS generator output and the oscilloscope as well. There is no change in the noise margin, which is equal to half the I height. Optimum sampling time is the midpoint of the data bit. In this case, it is 200 nanosecond from the rising or falling edge of the bit. The crossover of the rising and falling edges of Vout occur at the midpoint of the I height when VTH is set at the optimum level. This will be explained detailedly in the next slide. So in this slide, we are going to see about the generation of the I pattern on VOP and Vin. In this experiment, I pattern for the input Vin and the pin diode output VPO of the fiber optic digital link will be studied. VPO is an analog voltage as shown in the block schematical in the previous section. VPO results from the photocurrent through the pin diode, and it is appear across the built-in Orin of 5.1 K. This experiment may be repeated for other settings of Orin down to 1 K. For the built-in Orin, the experiment will be restricted to PRBS speed of 500 kilobits per second and 1000 megabits per second. Since the free amplifier and comparator do not have a role in this study, to isolate this component, VTH will be set to one of the extreme settings from 0 volt or 0.6 volt. This will ensure that no transition occur on the comparator. Next, you are going to see about the procedure to generate I pattern on VOP and VIN by the following steps. Step 1. Turn the trainer on. Connect the optical fiber cable as shown in the diagram. Connect oscilloscope CH2 to VIN and CH1 to VPO. Use CH2 as the trigger source for the oscilloscope. Set VTH to 0 volt TC by turning to the fully counterclockwise position. Step 2. Set select to the PRBS 500 kilobits per second mode. Set oscilloscope time base to 1 microsecond per division. Set Y amplifiers to CH2 to 2 volts per division and CH1 to 200 millivolt per division. So in this DSO digital output, the I pattern of VN and VPO is observed at the mode of 500 kilobits per second, where CH1 connected to VPO and CH2 connected to VN, and the respective I pattern is displayed in the DSO. Next, you are going to see about the step 3. Now increase the persistence settings of the oscilloscope to as high a value as possible. In a DSO, 10 seconds will be reasonable. In analog oscilloscope with no persistent control, one may increase the intensity until a pattern shown in the next slide appears. The I pattern for the transmitted train VIN on CH2 and the received train VPO on CH1 will be different from the one studied so far. While the I pattern for transmitted train VIN remains on ideal one, the I pattern on VPO will be a partially closed one due to timing and amplitude distortions through the medium of transmission. This waveform is a typical representation of the high-speed, long-haul fiber optic digital transmission systems where both timing and amplitude distortion occurs. A number of measurements may be made on the I pattern shown above. The optimum level of the comparator reference voltage VTH will be around the midpoint of the I height. In this case, it is 300 millivolt. At this setting, the crossover point for 1 to 0 and 0 to 1 transitions, even for Vout, will occur at the middle voltage, thereby reducing the timing jitter. The timing jitter is not a measurable here because the X sweep rate is very high at 1 microsecond per division. Rise time TR and fall time TF are measured as 600 nanosecond for this analog section. The speed up at the digital output is achieved employing a high-speed comparator with a digital crossover take placing at the middle of the I height. So in this slide we are going to study about the other I patterns. I patterns on VIN and VPO may be studied at other baud rates and other settings of the oscilloscope X sweep rate, as shown in the two DSO screenshots in the upcoming slide. I pattern with lower values of R in employing MF or fixed resistor across VPO and ground may also be studied. One may use resistors in the range 1.2K to 5.1K for this purpose. It must be noted that while the bandwidth will increase in direct proportion, the amplitude of VPO will reduce inversely. Eye patterns on VN and VPO may be studied after VTH is set for optimum performance as described in the earlier section, followed by the procedure for set up the eye pattern as shown in this section but without disturbing the VTH. The eye pattern on VPO will be a squarer but a little distorted when the high speed comparator switches level. This is due to loading of the comparator inputs. This eye pattern will have an improved TR and TF thorough. In this slide, eye pattern of VN and VPO PRBS observed at the mode of 1 megabits per second, where channel 1 connected to VPO and channel 2 is connected to the VN, and the respective eye pattern are observed in the DSO. I thank the management of the PSNA CT, particularly AC department, to organize this online spoken FTP on Advanced Communication Laboratory, and also I thank the Telenet system, MS equipment and the faculty development program team for their entire support to proceed this event into the grand success manner. Thank you one and all watching this video.